Chapter 4 starts chemical reactions, but the primary focus is stoichiometry. But a lot of the stoichiometry is very similar to what you had in Chem 4, so we'll just be looking at some of the differences. And I'll let you look at the standard stoichiometry problems in your homework. If you have any questions on those, you can ask me next time. But let's look at some of these reactions that we have in here. We aren't going to balance these because balancing just takes time, but eventually we'll figure it out. We're going to look at this type of reaction here. What type of reaction is that? 1A. From Chem 4, how would you categorize that? You'd call it a decomposition. So this would be a decomposition reaction, but you had different subcategories of decomposition reaction. You had decomposition into the elements, you had decomposition into element plus compound, you had decomposition into compounds. Do you want to memorize all those subcategories? Now, what we're going to do in Chem 1A is we're going to come up with a different categorization scheme in which we combine some types and separate some types, because there are different types of decomposition reactions, that we observe. There's redox decomposition reactions and acid-base decomposition reactions, which are both common, but the characteristics of those are quite a bit different, so we wouldn't classify both as being the same type of reaction. If you had a redox decomposition, it's really not the same as an acid-base decomposition. And so here, what kind is this? Well, it's easy to tell if it's a redox reaction. You know how we tell if it's a redox reaction? The oxidation state changes. And so we look, did the oxidation state change? So we're starting off with, what is the name of this stuff here? Yeah, sulfur trioxide, it goes to sulfur dioxide and oxygen. I can look at this reaction and immediately see it's a redox reaction. How? Because I see an element. Elements have an oxidation state of 0, but you aren't going to see zeros for oxygen in a compound. So automatically I see it's a redox. But let's go ahead and figure out the oxidation states anyway. Oxygen is -2, you have 3 of them, so it gives us a net charge of -6. This must be sulfur in the +6. And so let's see what happened. Sulfur went from +6, now we have sulfur here in sulfur dioxide. Oxygen is -2, so that means sulfur is +4. And then so we went from +6 to +4, which means it gained electrons. But where did the electrons come from that it gained? It had to come from somewhere. Where do those electrons come from? You see? The electrons must have come from, well, there's only one place where the electrons can come from, and that would be the oxygen here. Oxygen is -2. And here we went from -2 to -2, so there's no change for some of those. But for some of the oxygens, it goes from -2 to 0, so it lost some. And so this is kind of an unusual compound in which the oxidizer and the reducer are in the same compound. And we saw that before, the oxidizer and the reducer being in the same compound. Do you remember the compound where the oxidizer and the reducer were in the same? No? All right, let's go on to B. What's the name of this stuff? Cl2O7. dichlorine heptaoxide. We have to be careful because sometimes they drop, a vowel. Like, rather than saying heptaoxide, they might say heptoxide. Or rather than saying monooxide, they might say monoxide, like carbon monoxide, rather than carbon monooxide. And so this might be pronounced dichlorine heptoxide. Drop the A. And water yields, what's this? HCl4. Yeah. Perchloric acid? Perchloric acid is correct. And so what kind of reaction is this? And maybe in Chem 4 you'd call it a double replacement reaction? Single replacement? Acid-base neutralization? Gas formation? What kind of reaction is it? Well, in Chem 4, you probably would have called this a combination reaction. It looks like we're combining two things to form one. But is this a redox reaction here? Combinations are usually the reverse of decomposition reactions. So if we reverse this, that would be combination, right? And so is this a combination redox reaction, or what is it? Well, the easy way to determine if it's a redox reaction is just look at the oxidation states. So take a look at the oxidation states and tell me, did the oxidation states for any of the atoms change? Yes? No? Well, what's the oxidation state on oxygen here? Chlorine? Oxygen? Actually, do we do hydrogen or oxygen first? Hydrogen? +1. Oxygen? Chlorine? +7. And so chlorine didn't change. How about the oxygens? Well, that's -2, -2, -2. Oxygen didn't change. Hydrogen didn't change. Nothing changed. So is this a combination redox? No. This is what we call a combination acid-base. And since combination is not a unique category, for example, if you have a combination reaction, we don't know exactly what subcategory combination is. We want things that are unique. And so, for example, this would be just called an acid-base reaction. An acid-base reaction. Even though it's kind of tricky, it doesn't look like it. But, this is perchloric acid, and that's in there. So, something's happening here. Perchloric acid is a special acid. It is a strong acid. Strong acid would be like HCl. HCl is a strong acid, right? And so perchloric versus HCl. If I had both those acids in water, which one's stronger, perchloric acid or HCl, hydrochloric acid? Let's say I had a 1 molar perchloric acid versus 1 molar hydrochloric acid solution. Which is a stronger acid? Perchloric or hydrochloric? Turns out they're the same. And so hydrochloric and perchloric acid are the same strength in water. But perchloric acid, we classify that a little differently. perchloric acid, we call this an oxidizing acid versus hydrochloric acid. Hydrochloric acid is just mineral acid. And what is the reason why? Because both are strong acids, so that's okay. You know, you want to avoid spilling strong acids on your fingers, right? But you know, I've spilled hydrochloric acid on my fingers a bunch of times, and sometimes it burns a little bit, but most of the time it's no big deal. Just wash it off, right? Same thing with perchloric acid. You know, you spill a little bit on your fingers. It's like just like hydrochloric acid, right? Burns a little bit. Yeah, in certain respects, we'd expect it to be exactly like hydrochloric acid. But in other respects, I would worry because perchloric acid is what we call an oxidizing acid. Hydrochloric is just a regular old acid, mineral acid. And so what's the special distinction there? The special distinction has to do with its oxidizing ability. What do we call perchloric acid? Do we call that electron poor, electron rich, or just neutral? Perchloric acid. Electron poor, why? I'm sorry? It's an oxidizing acid. Oxidizers are electron poor. And so what makes HClO4 electron poor? Anybody remember from yesterday? It was yesterday, long gone, distant memory. Anybody remember anything special about perchlorate? No? It doesn't ring any bell? It rings a bell, Karen?
Yeah, it just needs a little bit of a push to get it started, and then it'll consume everything.
Yeah, if there's something around to consume it, you know. And so you don't want to mix perchloric acid. The stability is relative to something else, you know. Perchloric is fine. Perchloric is stable unless you mix in what? A reducer. Right? If you have a reducer, then it's going to be unstable. But just being you know, it's like hydrogen. Hydrogen mixed with argon, stable. No problem. Hydrogen mixed with oxygen, unstable. What's the difference? Well, argon's not going to react with anything. Same thing with something like hydrogen mixed with nitrogen. Hydrogen mixed with nitrogen, no problem. Hydrogen mixed with nitrogen, well, nitrogen is called sometimes a pseudo-inert gas because it's so unreactive. Why would nitrogen be so unreactive? In some ways it doesn't make sense because, you know, hydrogen mixed with oxygen is dangerous, right? Hydrogen mixed with fluorine, what do you think? Hydrogen mixed with fluorine is super dangerous, right? It's super dangerous, why? Because fluorine is the most powerful, the oxidizers. Fluorine really wants an electron. Fluorine's highly reactive. Did I show you the fluorine chemist handshake? Yeah? It's because it's so reactive. And so hydrogen mixed with fluorine, I mean, fluorine catches stainless steel on fire. And stainless steel is known for being chemically resistant to corrosion or attacks. They have different grades of stainless steel. Like some stainless steel is like 430. That particular alloy is not highly corrosion resistant, whereas, you know, 304 is much more corrosion resistant. They have surgical grades of stainless steel. But fluorine's very reactive. Fluorine is also the most electronegative element on the periodic table. What's number 2 in terms of electronegativity? Oxygen. Oxygen is a powerful oxidizer. It really wants electrons. What's number 3? Which one? Nitrogen. So, hydrogen mixed with nitrogen, isn't that a dangerous mixture? Dangerous. In fact, this room is filled. You know this room is filled with 20% oxygen, 80% nitrogen. What are you going to worry more about, the 20% oxygen or the 80% nitrogen? Is attacking. You know, we live in a very oxidative atmosphere. You know. And so the oxygen in the air will corrode things like steel. Everything gets corroded in this atmosphere. Or is it because the corrosion's because it must be the corrosion must be because of the oxygen and the nitrogen, because nitrogen is number 3, right, on the list of electronegative species. Nitrogen really wants electrons also, doesn't it? Being so electronegative. And so we're being hit right now. We're being hit with oxygen and nitrogen. And so, you know, people used to worry just about oxygen, so you better increase your dosage of antioxidants to compensate for the nitrogen. Or has that already been factored in? What do you think? And so, well, if somebody told you this, that they're selling some supplements to help you prevent damage from nitrogen in the air, because there's so much nitrogen in the air, you know, they have some supplements to help you counter the damaging effects of oxidation due to nitrogen. In fact, maybe we should stop calling it oxidation, because air is 80% nitrogen. Maybe we should start calling it oxidation, nitridation, you know, to give nitrogen its due as a powerful oxidizer. What do you think? Well, that's probably what we think based on theory, but that's all wrong, right? Because the experimental fact is nitrogen is what they call a pseudo-inert gas. You know, nitrogen is extremely unreactive. And so why the heck would nitrogen be so unreactive? Nitrogen is not what we consider a strong oxidizer, or a powerful oxidizer. And the reason why is because of the, I mean, it could potentially oxidize stuff, but it doesn't react much because of the strong nitrogen-nitrogen triple bond. And so to break that triple bond costs a lot of energy. And so nitrogen is quite stable, the molecule itself. And so it's not terribly reactive. But this, you know, HClO4 is terribly reactive. It's terribly reactive when exposed to reducing agents. And so therefore we don't call it a regular acid, we call it an oxidizing acid. Oxidizing acids, you have to be careful with what you mix them with, you know, because strength is all relative. Strength, you know, these judgment calls come from experience. So for example, if somebody were about to do an acid-base titration and they got the burettes set up there, would you say, hey, stop, wait a minute, you need to put an explosion shield between you and the burette, because if you mix strong acid with strong base, you're going to get an explosion. They're mixing strong acid like HCl with a strong base like sodium hydroxide. You got to worry about an explosion? Yes? Sometimes you got to worry about like a steam explosion, too much heat being generated. For example, there's a rule that they teach in chemistry. It's AA, add acids. Always add acids to water. Never add water to acid. You add acids to water because a lot of heat, it's an exothermic reaction, so a lot of heat's generated, and the water acts as a heat sink. So as you slowly pour the water in, heat's generated and that heat is dispersed in the water. If you do the opposite, you add the water to the acid, then you add 1 drop of water, hits the acid, so much heat's generated, you don't have much of a heat sink. Just that 1 drop of water will absorb a tremendous amount of heat, superheat, and come off as a little steam explosion. That little steam explosion kicks up concentrated, this is for concentrated sulfuric, not dilute. It kicks up the concentrated sulfuric acid, and sometimes it lands on your fingers or your arms or whatever. And it causes burns, up to 3rd-degree burns. And so I'm not saying it's not dangerous, but as far as relative reactivity goes, you see, when we're dealing with an oxidizing acid, we have to be careful, because when we're dealing with a normal strong acid, we all have experience with that, right? And now you tell me, perchloric acid, what can you tell me about that? Is it electron poor or electron rich? Perchloric acid, this stuff. Electron rich? It's electron poor. It's electron poor because of the chlorine. What's the oxidation state on chlorine? 7. You look at the periodic table, +7 oxidation state on chlorine means what? It has no valence electrons. It lost all 7 of its valence electrons. How many +7 cations do you know? How many what's the highest charged cation you know? +3, right? Well, if you have something that's +7, how stable do you think that is? Not very. The way we get a +7 is because we have oxygens, bonded to this, which helps reduce the charge. But, if we're looking at a +7 on chlorine, that's not so happy, meaning that perchloric is a strong, what? Oxidizer. But we have to put things in perspective, because you don't want to use strong. A strong oxidizer is like a strong acid, right? Or is it? No. We have to put things into perspective, And so this is an oxidizer. How about this? Rust. Is rust a strong oxidizer? Or a reducer, or neither? This is rust. Fe2O3. Iron 3 oxide. Strong oxidizer? Strong reducer? Neither. If you were to pick one, what would you pick? Oxidizer or reducer? Reducer? Why would you pick reducer? Anybody? Or oxidizer? Why would you pick oxidizer? Well, you'd look at the oxidation states. What are the oxidation states? +3 and -2, meaning what? It's a strong, it's a reducer because oxygen is -2. It's an oxidizer because iron is a +3. Or both, maybe. Which way do you want to lean? What do you think it's better at? Hmm? It's a better, yeah, oxidizer. Why did you say that? What did you say? Plus 3 versus minus 2, so it's just the magnitude of the numbers, right? Well, it's not just magnitude of numbers. You have to put a little more description on them. And that is, minus 2, is that an unusual oxidation state for oxygen? No, and we've seen a lot of stable compounds with minus 2 on oxygen, like carbon dioxide. You know, if carbon dioxide were electron rich because of the oxygen, then that means carbon dioxide should burn, right? So fuel. Does carbon dioxide burn? Is it flammable? No. Carbon monoxide is flammable, you know, but it's not because of the oxygen. Carbon monoxide is flammable because of the carbon. Oxygen doesn't play any role in this. And so this is just memorizing things. You just memorize just experimental facts, and then you can put things into perspective, because in learning chemistry we have our two-pronged approach. You can't do everything off the theory. So when we're looking at the numbers, we can't say a +2 versus a, you know, +3 or on two different atoms, or a +2 versus a -1. You know, it's hard to put the numbers and put a meaning on those quantitatively. We do this qualitatively based on what we've observed. And so for something like iron, yeah, I'd expect this to be an oxidizer. A strong oxidizer? Rust? You know. A strong oxidizer, let's say, maybe not. Right? Maybe not. I don't really think of it as being a strong oxidizer. How about aluminum? Solid. Electron rich, electron poor. You know, aluminum solid, what's the oxidation state on aluminum? 0. Aluminum metal. 0. And so this is our electron poor atom, and aluminum would be electron rich, you say? Or neutral? Well, you know, this seems much more electron rich, because this is -2 versus a 0. And so -2 seems much more electron rich, doesn't it? But it depends on the atom. A -2 charge on oxygen versus a 0 charge on aluminum is different. And so even though aluminum is 0, it's electron rich. Why is aluminum electron rich? Well, all metals are electron rich, right? All metals. And so we have a potential redox reaction occur here. Now, what do you think about the strengths of these particular? Is aluminum a powerful reducer that is extremely electron rich? Reacts? Nah, the aluminum seems pretty stable. Right? How about rust? Rust seems pretty stable too, you know, and so I have this aluminum tray here, and I have this rusted out thing, and they both seem pretty stable, don't they? In fact, I have my rust. I'm going to rub the rust on the aluminum and see if something happens. But I don't see much happening here. But it always depends on the conditions too. And so to put things into perspective, you know, let's look at perchloric acid. Perchloric acid versus rust. Which one do you think is a more powerful oxidizer? Perchloric acid or rust? Or about the same? Perchloric? Okay, how much stronger do you think perchloric acid is versus rust? Much stronger? A little bit stronger? Much stronger? Yeah, I would think perchloric is much stronger, much more powerful of an oxidizer. Why? Because of the +7. The +7 is highly unstable. I mean, I've seen +3 before. Aluminum +3, right? Iron +3. But +7, that's special, isn't it? And so I'd say rust is a lot weaker than perchloric acid. And so let's take a look at this reaction here. Rust plus aluminum. If you haven't seen it before, maybe a lot of you have seen this reaction.
It's a powdered mixture of iron oxide and aluminium, which when ignited burns at 2,500 degrees Celsius, which is very, very hot. This is liquid nitrogen. It's specially stored at -198 degrees Celsius. That's 163 degrees colder than the North Pole in winter. But is it cold enough to neutralize the intense heat of thermite? Into the slow release mechanism of a garden flower pot, the thermite is ready for action. Just like the touch paper, stand well back. The fuse triggers the irreversible thermite reaction. Scorching hot meets freezing cold, a fierce battle rages. The smoke clears, and incredibly, nothing remains. As the thermite burns at 2,500 degrees, it releases a raging torrent of molten iron, which rains down on the liquid nitrogen, boiling the glacial mixture away in a pool of vapor and melting the cylinder, leaving just a couple of white hot iron. A clear victory for thermite. So there you go, Dan. Adding something cold to thermite doesn't cancel it out. It just makes it angry. Thermite. You won't like it. This is a car. It's been specially chosen to be destroyed because it's old, it's white, but more importantly, because it's French. The engine block is the densest part of the car. It's basically a huge lump of metal, and, well, it's very hard to melt. Lucky then, the Brainiacs have plenty of thermite, specially packed into the slow-release mechanism of a garden flower pot. A big pile on the bonnet directly over the engine block should do the trick. Time to light the fuse and give this homage to French engineering the send-off it so richly deserves. The irreversible thermite reaction begins. Seconds, the fiery concoction eats through the bonnet, spraying molten thermite into the engine beneath. The devastation continues inside until finally a torrent of white-hot liquid metal pours out of the bottom, signaling the inevitable victory for thermite. A quick check confirms a clear path of destruction through the engine. Now that the engine is melted clean through, it seems only fitting to have a go at the petrol tank. Packed into the slow-release mechanism of a garden flower pot, the thermite is ready for action. Hopped onto the roof, directly above the fuel tank, the topper, and just 4 feet of family car stands between the thermite and 8 gallons of petrol. Like the touch paper, a stand well back. The irreversible thermite reaction begins. Thermite produces a stream of molten iron which melts through the car in seconds. It's 2,500 degree heat igniting the expanding petrol in a devastating fire, leaving behind a car that won't be going very far anytime soon. So there you go.
So we have a special distinction for acids like this. Even though it's a strong acid like HCl, this is nothing like HCl. You know, HCl is +1 for hydrogen, -1 for chloride or chlorine. This is oxidizing acid. Oxidizing acid, you have to be careful with what you mix it with, right? Because redox reactions are potentially very violent. It's not that, like I said, it's not that acid-base reactions can't be violent. You know, the sulfuric acid is one example, but it's a different kind of violent. You know, generating a lot of heat and steam versus a lot of energy here. And so this is a redox reaction. Let's look at this next reaction. What would you classify this one as using Chem 4 classification system 1C? Is that a double replacement reaction? Single replacement reaction? Acid-base neutralization? Effervescent reaction? Combination reaction? Decomposition reaction? What is it? Well, pretty soon you're going to run out of categories, right? And so you're going to have to add more categories to the Chem 4, but we don't, because we can easily categorize this as a, well, what's happening with the oxidation states? What is this compound here? This is nitrogen dioxide. What are the oxidation states? Nitrogen dioxide. -2, yeah. Not +5. +4. -2 and +4. Water is 1 and -2. How about nitric acid? What are the oxidation states here? -2, +1. Here you go, +5. And then this one, what is this called? Nitrogen monoxide. Nitrogen monoxide is -2 for oxygen. What is it for nitrogen? No, not 3. +2. And so what happened to nitrogen here? It went from +4 to +5, and also +4 to +2. Uh-huh. Because the oxygen is -2, and therefore nitrogen has to be +2. And what happened to water? Nothing, because this went from +1 to +1, this went from -2 to -2. And so nothing happened to water. And so who's the electron-rich species? Who's the electron-poor species in this particular reaction? This is tricky because the electron-rich species was nitrogen. The electron-poor species was nitrogen. And so some of the nitrogen atoms acted as electron-poor, some acted as electron-rich. You learned about this kind of reaction maybe in Chem 4. It's called disproportionation reaction. But it's a tricky one. Nonetheless, this is a redox reaction. In fact, nitric acid is often associated with NO. This is a common product. When nitric acid reacts, NOs. NO is nitrogen monoxide, or nitric oxide, which is colorless. It's a toxic gas. And the NO is quickly oxidized to NO2. NO2 is a brown-orange gas. And so in Texas City, the orange plume of smoke was NO2 gas being generated. You know, the guy said he smelled sulfur, but it wasn't sulfur. It was oxides of nitrogen. Oxides of nitrogen have that particular sense of smell, and it's very accurate as well. When we look at this, is a redox reaction. And so we aren't going to subclassify. In fact, what we're going to do is we're going to classify reactions based on 3 categories: redox, acid-base, and double replacement. Except I'm not going to call it double replacement because double replacement might not be so obvious. So we're going to use another name for it, metathesis. You know, double replacement is you're always looking for the form AB plus CD, but sometimes you get mixed cation salts, like potassium and sodium mixed in there, and so you have more than two compounds reacting. You know? So that complicates things. Well, this next reaction could be called a double replacement. You know, sometimes we could tweak this a little bit. And so here's our AB, PCl3. And if we treat water as H plus with hydroxide, then this would be a double replacement, because what we'd have is, oh no, this is not a double replacement. Do you see that? Because otherwise we form some kind of hydroxide of phosphorus and HCl. We got the HCl here, but this is not a hydroxide. This is, what is this called? H3PO3. This is phosphorus acid. Good. And in this particular reaction, is this a double replacement? No. Is this a... What other categories of reactions are there? Is this an acid-base reaction? Or is this a redox reaction? Well, the first thing we'll look is it a redox reaction? It's very simple to tell if it's a redox reaction, because only redox reactions will show a change in oxidation state. Acid-base reactions and metathesis, or double replacement reactions, the oxidation states do not change. And so did the oxidation states change? If they did, it's a redox reaction. If they didn't, then it's an acid-base or metathesis, i.e. double replacement. And so let's take a look. What's this called here? Phosphorus trichloride. Chlorine is in what oxidation state? Chlorine is -1. Phosphorus is +3. Let's go to this one. Let's look at phosphorus acid. Hydrogen is oxygen, phosphorus. So -6 plus 3 is -3. This has got to be +3. So we went from +3 to +3. Chlorine went from -1 to -1. Hydrogen went from +1 to, this is +1, this is +1. Oxygen went from -2 to -2. So none of the oxidation states changed. This means it cannot be a redox reaction. That means it's either a double replacement reaction, but we eliminated that. It's not a double replacement reaction, meaning that must be a acid-base reaction. You know, it doesn't look like your standard acid-base reaction, you know, where you have a base and neutralize it with an acid. But you know, nor did this one. You know, recall that B is also an acid-base reaction. You see that? But we have different definitions of acids and bases. One definition is the Bronsted definition, which is a proton donor and proton acceptor. But we have a more general definition, which is Lewis. And Lewis described acids and bases as electron pair donors and acceptors. And so acid-base reactions can get a bit more complex. We'll look at those. All right, let's take a look at this. How would you name this?
Diphosphorus tetrafluoride.
Tetra what? Tetrahydride? Yeah, diphosphorus tetrahydride. That's correct. This is going to, what do you name this? Phosphorus trihydride. How do you name this? Is this tetraphosphorus or just phosphorus? Phosphorus? Yeah. This is what we call white phosphorus. There are different allotropes of phosphorus. This one occurs as 4-atom cages of phosphorus, white phosphorus. White phosphorus turns out to be unstable. Usually you stabilize it by putting it underwater. If it goes out of water, it starts to glow as it starts to combust slowly with oxygen and air. Anyway, what kind of reaction is this? Immediately, you know, I can tell this is a redox because I have element here with 0 and phosphorus and compounds. And it's not going to be 0, I think, in either of these. In fact, what's the oxidation state over here? +2. The oxidation state here? +3 and 0. So who is the electron poor species and who is electron rich species? Because in redox we have a transfer of electrons from the electron rich to the electron poor. And so in this particular redox reaction, who is the electron poor and who is electron rich? Well, this is another one of those odd disproportionation reactions. What is a disproportionation reaction? Well, can you see who the electron rich? Which one? So who is electron rich? Phosphorus. Who's electron poor? Phosphorus. And so phosphorus acts in both roles. Some of the phosphorus atoms lose, some of the phosphorus atoms gain in this disproportionation reaction. In disproportionation reactions, you know, the net, what we have at the end is more stable than what we began with. So, you know, the +2 oxidation state on phosphorus isn't so stable, apparently, you know, compared to +3 and 0. All right. How about B, 2B? What kind of reaction is that? This is your Chem 4 style combination reaction. In Chem 4 you did the element plus element combination. You might have done an element plus compound combination and a compound plus compound combination, depending. But this one's going to be, well, we don't have to call it a combination. We could call it a redox acid base or metathesis, double replacement. This is going to be a redox reaction as well. White phosphorus plus chlorine yields phosphorus trichloride. How about C? What kind of reaction is C? This is a double replacement. And so this particular reaction, you know, we have the iron 3, it stays as iron 3. Do you see the oxidation states don't change? Chloride stays as chloride. Sulfide stays as sulfide. Hydrogen ions stay as hydrogen ions. And so the oxidation states did not change through here, meaning it's not redox. And therefore it must be either acid-base or double replacement. Well, this is double replacement, AB plus CD. Do you see the pattern? And so this is what we call a metathesis reaction here. So let's name them. What is this called? Iron, Roman numeral 3, chloride. Give me another name, the old name. Is that ferric chloride or ferrous chloride? Ferric. Ferrous is iron 2. Ferric is iron 3. It goes to the higher charge. Name this. You'd call it dihydrogen monosulfide or dihydrogen sulfide, maybe. Nobody calls it dihydrogen monosulfide or dihydrogen sulfide. You know what they call it? They call it hydrogen sulfide. Hydrogen sulfide is a very toxic gas, and it smells like rotten eggs because hydrogen sulfide is produced in rotten eggs. It's very toxic and it's a very lethal gas because even though it's easy to detect the odor of hydrogen sulfide, the H2S ends up desensitizing your nose, so you begin to lose your sense of smell to H2S. And so people have been killed because they thought the H2S is dispersed, but it was just that their nose couldn't detect it. It was saturated, the receptors, or, I don't know, fatigue. If we take hydrogen sulfide and dissolve it in water, which this is, all these are aqueous, then we have another option. We could name it as an acid. And so hydrogen sulfide would be called what acid? Not sulfuric. Sulfuric acid is H2SO4. Hydrosulfuric acid. Hydrosulfuric acid is correct. The sulfide goes to hydrosulfuric acid. What's this called? Iron 3 sulfide. What's this called? Okay, in aqueous solution it's called hydrochloric acid. But, you know, HCl can be driven off as a gas. And as a gas, we don't call it necessarily hydrochloric acid. We call it hydrogen chloride gas. Right? Hydrogen chloride, chloride makes hydrosulfuric acid. Sulfide makes hydrosulfuric acid, according to the rules. There's a double replacement reaction here. How do you name this one here? Mg3N2. This is magnesium nitride. Water, this is magnesium hydroxide and ammonia. What kind of reaction is this? Maybe it's a redox reaction. And so we should take a look at the oxidation states first. The oxidation state on magnesium is +2, that means nitrogen is not -2. Nitrogen's -3. It's the nitride ion. Hydrogen's +1, oxygen's -2. Magnesium is +2, oxygen's -2, hydrogen's +1. Over here, hydrogen's +1, nitrogen is -3. And so if I look at all those oxidation states, none of them change. This is not a redox reaction. If it's not a redox reaction, then what is it? Acid base or double replacement metathesis? Well, turns out this could be an acid base reaction. Sometimes there's overlap because this is actually an acid base reaction, but it could be interpreted as a double replacement reaction. Because if you treat water, H2O, as the compound HOH, you know, you have a hydrogen ion and a hydroxide, then we can take the hydroxide from water and give it to magnesium to form magnesium hydroxide. And then we take the H plus from water and give that to nitride, which forms this. And so in a way it's like a double replacement reaction, or it can be thought of as a double replacement reaction, but technically we'll call it acid-base. None of the oxidation states change. All right, so let's stop here. We're going to take a break and then start again in a little bit.